So because of the storm, obviously I don't have whiteboard behind me. I don't have your cash totals in front of me, so it'll be tricky to bet. You can, if you want, write it down and or maybe put it in the chat and I'll like save the chat. I don't know.
We'll figure something out.
We can try something. Can you hear me okay?
Yeah.
Okay. I will try today. If it's not working or if the whiteboard's too slow or anything, just be like, all right, this was fun, Dr. Krismani. Let's do it when there isn't an epic storm. I was looking at some of the flood warnings, and it looks like the flood warning, at least for my area, is through till tomorrow. I don't know how that's going to reflect on the rest of your classes for this week, but my hope is that you'll be able to go to some of them. Anyone have Tuesday classes?
I do.
Okay. 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 So, all right. So, should we just jump in? Is that a quorum? Anyone want to share their storm stories first? Anything weird happened so far?
No, it's just been raining for the past 8 hours because I remember it raining when I went to bed. That's mainly it on campus. I know
Yeah, I
it's
guess
very riveting.
on campus, the commute wouldn't be too bad.
My house has a leak in it, and the owner is very slow to fix it. So there is just a tarp with bricks draped over the top of our roof.
Praying for you, John.
Yeah, it's okay.
You have like one of those traditional buckets underneath, collecting and then throwing it out and then collecting.
No, it's right along the edge of a wall, and nobody was living in that room, so we didn't realize how bad it was getting. But now it's like seeped into the wall. Yeah. Yep. It wasn't until we were like, huh, why does it sound like there's like water flowing?
Yeah, because there was.
There was.
Wow, that's
Yep.
creepy.
Yeah. That's it.
So
Okay.
fun.
Anyone do anything fun this weekend?
Not with this fucking rain.
Yeah.
Can't do anything.
Yeah, that's true. I don't know. Sometimes, so I watched Saltburn. That was fun.
Oh, geez, yeah.
I was gonna do. I was gonna
Still
build
don't know what
Lego.
Saltburn is.
What's that?
Well, it's a lot.
Yeah, that's
Still
correct.
watch it.
Exactly correct, John. Okay. On that note, all right. So we're gonna be reading out of the good book today. And I'm gonna try and do some stuff on the whiteboard. But before we do that, let's think about some motivation. So we'll try a couple bets here and we'll see how well this goes. And of course, if it doesn't, if the betting doesn't work out, that's fine. We can just try. So let's ask the first question. And this is the one that you've been thinking about all weekend, I hope. You go to a bar or you're at a party with a bunch of friends, right? And the gambler walks up to you. And he says, let's say there's 25 people in the room. And he says, I'll bet you $100 that 2 people in this room share a birthday. You take the bet?
Ooh.
No.
No.
Anyone else? I can't see hands, so maybe like pop it in the chat or something. I can't see faces either.
Negative.
So no one's taking anyone taking the bet? Okay, let's try this a different way. What about if there are, let's try a real bet here. Okay. If I tell you you're in a bar, 20 people are there, and he says whatever amount of money that you guys want to bet, and they say, I bet that no 2 people in the 20 will share a birthday. Or sorry, he bets that that 2 people do share a birthday, and you bet no. So your bet is that they don't, and his bet is that they do. Does that change anyone's mind?
I feel like it does for me. Although I have a twin, so he can't be there.
Yeah, let's go ahead and assume that you don't know anyone in the room, right? It's like a work party that you've never met anyone before. Trinity's put $1 on the line.
I'll put 10 bucks on it.
Okay, Rolando's got 10. Sarah's got a 1. Anyone
No
else?
big spenders.
Isabel? Is that it? John, you can't bet 0.
John.
You can only bet or not bet. Bet
think I
negative
still won't.
$5.
Yeah.
Can I bet $10 that 2 people would share a birthday? So you want to bet $10 and Reed, you think 2 people will share a birthday? And everyone else is betting that they don't have 2 shared birthdays in a room of 20 people. Is that correct?
I'll do that.
Okay. So everyone here would double their money except for Reed.
Ouch.
Rip.
Ouch.
No.
So the way that we want to think about this is let's do the easiest example. Okay. So let's think about 2 people in a room. What are the odds that they share a birthday?
What, like 1 out of 365?
Is that right?
That's my first impression.
Okay. So how do we calculate that?
We had to know how the total number of possible birthdays. That's why I have the 65 in the denominator. So
Okay.
365.
Okay.
And then in the numerator, it has to be 2 people, and they both have to share a birthday. So it's probably something like a probability of A of A when given B or something like that. Is it?
Okay, so let's have a look, right? So one of the places that we can start is to think about this in the context of sample spaces, right? So if we have some sample space, and you can see this drawing, I hope.
Yep.
Okay, so this is all the days, right? Wait, Rolando, I can see your guys' cursors for some reason. It's very distracting.
Yeah, we get right too.
Oh, stop. Get off the screen.
Oh,
How do I disable this? Board, lock board.
No.
Did it work?
No, hold on. I don't know because it removes viewing access. Oh boy. Collaborator cursors. Nope, that's gone.
There you go.
Okay.
Maybe.
I can still see them.
So whoever made a smiley face, please unmake that smiley face.
Oh no, it's still a thing. I thought
Okay.
that works.
Okay, guys, just don't touch it.
Just stay focused, lock in.
All right, lock in. All
Log
right.
in.
All right. We're gonna have fun today. I know that. Okay, so how many people are wearing real clothes? Let's just raise that hand.
Wait, what?
Yes.
Are there fake clothes?
Well, like pajamas.
Oh yeah.
I'll
I thought you
raise my
just meant
hand.
like clothing in general. Sorry.
So okay, all right. That's bolder than me. I'm in the pajamas today. So I'm gonna allow a certain amount of scribbling on the board, but up it to a certain point. Okay. So let's think about the sample space S, right? That contains how many days?
365.
Very good. Okay. So if we're constructing the probability, we have NS equals 365, right? Oh God. Anyway, that says that. All right. And how many days for 2 people do we need to match?
1 day.
Just 1. So the number of the outcome A that you want is 1. Right? So 1 in 365. So would you take that bet?
Yeah. You
Of
should have bet
course.
high.
Yeah, of course. Yeah, that's a great one. The chance that 2 randomly chosen people will have the same birthday is very low. Okay. Now let's say you go into a room of 400 people.
No, you're guaranteed to find somebody because it's 400 over 365.
Ah, now you're guaranteed to find someone. And so we used some other numbers. That's a big range there. We used 1 and we used 400. Now, what is the minimum number of people that you would be required to have in order to get a duplicate birthday? 100%.
Right? 2 to
365.
Is it?
That you would like guarantee?
Yeah.
Then it'd be 365 over 365.
But what if everyone's born on the same day?
Ah.
oh geez.
Well,
So Isabel is saying, what if everyone's born on each individual day of the year? Then no single person would have the same birthday. So you'd need a minimum of 366 birthdays. Such that one would overlap. 100%.
So true. So true.
Okay. So let's erase this. Let's see if I can figure out how to erase first. Okay. Oh God, this is gonna be so pedantic today. I'm sorry, folks. All right, so let's have a look here. And we're going to talk about probability distribution functions in a little bit. But we can see that the probability of two people sharing a birthday is very low for a small number of people, and somehow it changes, right? So how do we go about thinking about how many people there might be? We can go back to this idea of, we had all of those individual monies, right? Different color monies. And we could rearrange them, right? What was that called?
Permutation?
Combinations?
Correct. Permutations. Okay. So let's just refresh our memory a little bit. How many permutations are there for 4 objects?
Permutation for 4 objects, that's 4 factorial.
8?
So that's 6, 24.
4, and let's do this
Oh,
slowly
okay.
for the kids.
Yeah, 24.
4 what?
3,
Good.
2, and 1.
And I'll never put 1, right? But good. Good.
Cool.
Okay, and that's a number, right? Okay. Okay, and so let's say we want to pick a subset. So we said this before. We said, what about if K is less than N? We want to select all of the possible permutations. That is to say, we want to sample amongst those smaller subgroup. And I gave you this definition of N. Oh, let me say, oh, dang it. This, oh God. There we go. Let's call it little n instead of capital N. And we'll call it P like this. These are the permutations of the subset K. So here's the here's the whole set here. Oh my God, I should learn how to write cursive on this one. And this is the subset. Okay. And now how is that represented? How many permutations do you get? Does the question make sense?
Mhm.
Let's say this a different way. Let's say I have 4 objects, okay? But only 2 of them I want to rearrange. Ah, good job, Reed. Where did that come from? Don't say I'm reading the book.
The book.
Reed.
That's good.
We got to use our brains here. That is correct. That is correct. But remember that we want to be like investigating our own feeling. Unless you like read that earlier. But if you like reading along with me, then it kind of like. Okay. All right. So let's write this down. So what do we mean by this? Here's n factorial. What does that represent?
The whole set.
The whole set. Good. So that'd be 24 in this example.
Yes.
Good. And what's down here?
The set minus the subset.
Good. And what's that?
Guess 22 factorial?
Excuse me?
Or no. I'm sorry. I'm crazy. 2 factorial.
2 factorial, which is
2.
very good. Okay. So you might be saying to yourself, well, I know that number. That's our good old friend 12. So what happened there? So you have these 4 objects, I wish I had 4 objects that I could show you, right? We can slot those 2 anywhere that we want. We can move them around, right? But there's not an infinite number of variations, right? There's a subset of those variations. So let's think about this in the context of the birthday problem, okay? God. All right. How do I do this problem for 20 people?
Would it be that the set is 20 and then the subset you just need 2 people?
So 2 people what?
2 people to, I guess, have a birthday. I guess if you're the
Everyone
game
has a
developer.
birthday,
Oh, okay.
right? So we have to be really clear about what we're thinking about here, because we can trip ourselves up if we think about the wrong set, or if we think about the wrong sample, or right, there's just like numbers that we're just throwing around. So we want to be really careful about how we think about this. So what is it that we're asking again? What's the full sample?
I guess they want at least 2 people who share the same birthday.
Good. So at least 2 people that share the same birthday. Okay. So what's the full sample?
Is it the sample of the 365?
It has to be, right? Because that's where the days are going to be drawn from. Another way to think about this is that you can imagine you walk into a room and everyone has a card with a number on it. And that number is their birthday number. Like, you know, if you're born March 3rd or something, you're like 62 or something, right? And you would have a number on it. Does that make sense? And what are the odds that one of those cards matches? Does that make sense?
Mhm.
Okay.
Yes, yes, it does.
Okay, so what is our little rule say? It says that we have P, and then what goes down here?
20
2?
because we're only looking at 20 people.
Exactly. Okay. So we're saying to ourselves, what's the probability 20 is less than 3? Oh God. Sorry, let me finish this and then I'll make that less than sign better. Good. So 20 is less than 365. So this is telling us how many permutations there exist for 20 people who may share 365 birthdays. Different choices of birthdays, right? Okay, so what's that equal to?
A nasty number.
Good. All right. Good.
Mhm.
And we're not going to calculate it, right? Okay, so we're going to leave this up here. Oh, someone just went off the screen. I don't think it was me. I hope it wasn't. Okay, and on the bottom?
345.
Very good.
Yeah, factorial.
Okay. And we're not going to calculate that, right?
Hope not.
Okay.
It's a big number.
It's a big number. So now the question is, how do we get to the probability that all the birthdays are different? Let's write that again. The
Isn't
probability.
it just that minus the one you have?
So let's remember what we wrote up here. Oh my God. That's a L.
Pick it now.
Like a loss?
Yeah,
Sorry.
well, it's definitely a loss. Probability that all B days, oh my God, are diffy. Sorry, I'm just gonna write in cursive. Do people understand cursive?
Yeah.
All right.
Yeah.
What's the probability that all birthdays are different? This number here, is it a probability?
No, it tells us like
The
guess,
number
like-
of unique combinations.
Unique combinations of?
yeah.
Hmm.
20 people or 1 or 20 people. I don't know.
It's okay.
I don't have a stroke saying that one.
What's that?
Nothing. I don't know.
So it's a number. No, I think you're onto something. It's a number of unique combinations, focusing only on
Or
20 people. Out of 20 people, something like that.
Yeah, so this is the number of unique combinations, right? And the way that we want to think about this one in particular is that you have
It's like a parameter we've set, right? So that's like how we compare.
sorry, say that again.
It's like a parameter that we've set. So like we're like setting our own, I don't know if you would call it an axiom, but like our own rule for this problem. It's like we have to follow this rule.
Well, remember how we thought about the probabilities for having a sample when we had just like 7 colors, and what's the odds that they fall out of your pocket and land in color combination?
Mm.
Right? And then what was the probability if you had like the smaller subset together?
Mhm.
Right? So you use a combination of these probabilities. And in fact, you're hoping the probability that all birthdays are different, you want to make sure that none of those individual unique combinations match. Right? So that would end up looking like something like this, actually. P, oh God. Oh my God. Okay. P looks like this, 365 factorial over 345 factorial. Oh God, I'm so sorry, folks. Times 365 to the power 20 for the 20 people that you have, because you are multiplying this probability 20 times. That makes sense? 1 out of 365. And then you have the 20 combinations. Does that make sense?
Okay.
So the question is, the probability that all birthdays are different is represented this way. And what's the probability that at least one is the same?
Would it just be what you just wrote, but instead with the power of 1?
So this one says all 20 people have different birthdays.
Mm-hmm.
Okay, and that's going to be some number. And I would like to change my idea now, and I want to know what is the probability that at least 2 are same. Oh my God, sorry.
So
You'll
power-
notice I said this very specifically.
yeah.
I said at least 2, not exactly 2. So one of the tricks we're going to keep in mind here is if this is the probability that all birthdays are different, then this is, for example, you might think of this as like B. And if at least 2 are the same, then this would be a separate event, A, which would be 1 minus B, right? Or in this case, P. So what I mean by that is the probability that all birthdays are different is this set over here. And then all the other choices include at least 2, which are the same, right?
Okay.
Are folks getting that?
Yeah.
I just realized I can scroll. I can just scroll forever. Okay.
Also, I'm still a little bit confused as to the 365 to the power of 20 and the probabilities that all birthdays are different.
Okay.
Hmm. So so 365 factorial over 345 factorial, that is just the number of unique combos
Yes.
that you can just make out of that permutation. And then the reason why you put the 365 to the power of 20 is because out of a room of 20 people, you want it so that every single individual doesn't share a birthday.
Right. So let's go back a step and we'll think maybe if you have your cards in front of you, okay, and you want to put on top the number of outcomes that are good And on the bottom, you want to have the sample space. Okay. So remember, let's go back to our stack of cards and let's say, what's the probability that I get? I'm going to draw 4 cards. Okay. Or let's say I draw 1 card.
Okay.
What's the probability that it's an ace?
4 cards. One out. One
Four
out.
out of
It's 4 out of
out of
52.
52.
4 out
Right?
of
And you
52.
can do-
Oh,
you can divide that fraction down, but it tends, if we divide that fraction down before we think about it, then we're not remembering that that top number has a meaning,
Mm-hmm.
right? So here, when I think about the probability, here's the number of unique solutions. It's a big number, right? You know, like we talked about.
Mm-hmm.
So this is the top, so to speak.
Ah, okay.
And
Okay.
this is the bottom.
Okay.
Does that make sense? Because then we need every single person, every time that we draw a person, to have a unique birthday.
Okay.
Okay. Okay. So in practice, you would put this into Wolfram Alpha. You wouldn't do it yourself.
Yeah.
Okay.
Have you heard of Stirling's approximation? And
Yeah. That was, I think, we did that in StatMech.
okay,
I'm
good.
trying
So
to remember what it
I'm
was.
just gonna write it down here. I'm writing it from the book. because
StatMech?
I don't remember it. And this is just an easy way to write the factorial.
Yeah, assuming the n is large.
Yeah, sorry. So this is, I mean, if you look at it closely enough, you're like, wait, what? Where'd the E come from? Who knows? Okay. So it's interesting to note, if you do this and you go ahead and write this in, what is the n at which, or sorry, I wrote this wrong. What is the k? Oh my God, I'm so sorry. Oh. What is the k at which the probability becomes about a half? How many people do you need in a room for about 50-50 odds? If you read it in the book, you can just
Looks like everyone read it in the book.
Yeah.
yeah, I'm sure that's what happened. Okay. Not someone playing Smash Bros in the background.
No.
So
I
this
would
is
never.
this is what you have for the probability. And hashtag reading. Thanks, folks. So how high does the probability get for k equals 50?
K equals 50. So,
You have Wolfram Alpha, right?
I was gonna use
Why
my.
don't we calculate this out? We can either use this or you can use this up here.
Mhm.
Why don't you calculate it out for k equals 50 for me? Tell me what that looks like.
Okay.
Thanks, Rolando.
No problem.
Well, I think everyone's doing it, right?
Oh.
John. Thanks, John.
You just got a head start, that's why.
Hard to tell. I'm not looking in anyone's eyes.
There's my camera. Okay, so.
Are we staring at Sterling's approximation here? Is that what we're doing, or?
You're welcome to use that if you want.
Okay.
N is sufficiently large that the condition is valid here. I mean, obviously 365 N is quite big, and you'll notice that some of the numbers will be ratios of N's, but you don't have to if you don't want to. You can just put
Okay.
it in Wolfram.
Okay, deal.
I'm just gonna find a Wolfram. I can't find the factorial on my calculator.
I wouldn't try to do this on your calculator. I think it would be bad for your calculator.
I can handle it.
What calculator do you have?
He's got a
TI-89.
computer in his pocket.
Mm.
165. Although it is quite the hassle to even get like some of the more unique values, so not the best. Yeah, 65.
Had a very big number when I used Sterling's approximation.
But it was less than, the probability was less than 1, right, John?
Oh yeah, I guess if you is the idea do we place it so hang on. N factorial, is that when we use Sterling's, is that just going to be what we insert into P here? That
So
same
everywhere that you
approximation?
see a factorial, you would use the n factorial Sterlings if you wanted to. Yeah.
I see what you're saying. Okay. Okay. Yeah. Okay, now I see. Got it. So now I got it.
The 2
Okay.
pi's will cancel. It's the square root of 365 over the square root.
Oh, I got a decimal approximation.
Okay.
0.97.
Okay. Did anyone else do it? Sarah, Isabel, Trinity?
Wait, what what is Sterling's?
I can't hear you. What did you say?
What is Sterling's? What is that?
What is this approximation?
Is that what we're calling this?
So this is just a way, if you're not using Wolfram Alpha, this is a way to write these factorials, which are very large and will break your calculator.
Oh, I was so confused. I said, which one are we doing? Okay, I'll try right now.
Yeah.
And
What did you get, Rolando?
0.97. And that's when it's out of a room of 50 people that at least 2 share the same birthday.
Right. So 1 minus P, right?
Yes. Which is really good. Really good odds.
Okay, how's it going? Sarah, do you get anything? Oh, good. Okay, Sarah has a similar answer. Reed, have you calculated this? Or did you do all the work ahead of time? Ah, nice. 9.7. Okay, anyone get anything different?
Yeah, but I think it's because Wolfram doesn't like me.
Okay, okay.
Yeah.
So it's a crime, not a mistake.
Yeah.
Does this make sense?
I think it does.
In 50 people? I mean, 97, right? How much money would you put down on a 97% bet?
Oh, I put down all my money.
Okay, but imagine you go into a room. There's 50 people in the room that you don't know, right?
Mm-hmm.
You were with your rich friend, okay, from out of town. How much money are you putting down?
I'm gonna put down.
Am I the rich friend? No, Trinity. No, I am not.
I'm gonna put down like $500. No,
Isabel,
it's a
you'd be
97%.
willing to potentially be in debt $2 million?
Wow.
Yeah. Okay. All right. I mean, that's as sure as you're going to get, right? And that's somewhat, in my opinion, that's kind of surprising. You know, the number 23 is, in my opinion, it's not that high, considering that the distribution, right? If you think about it, right, it starts down near 1.365 like this. This is the minimum probability. And then it gets up to 50% here. Okay, and this is at 23 people. Oh God. This was at 2 people, right? And then it just like let me just draw it. It just plateaus, right? And it eventually heads towards 1. This would be 1. But here's 0.97 or 0.97. I should write that more clearly because the point's not really coming out here. This is just right there at 50. That's almost right where you started. And when does it finally get to actual 1?
Oh, let's go down. Let's check it out. When does it get towards 1? Put 100.
Did you say 100?
I'm gonna try 100.
No. These are memories, not our calculators. Correct. 366,
That makes sense.
right? So we only get that 0, or I guess 3% for the next 316 people that we had to the party. It's crazy, right? Okay. So let's think about another example. And this is one that, I would have loved to have done in person because then we actually would get to do it. Do people still have their cards with them?
Yes.
You have them
Oh
nearby?
yeah, I got my cards.
Does everyone have their deck with them?
Yeah.
Okay. So this is going to be the hardest one because I need someone to make sure that you're not cheating, but also I'm going to ask you to gamble by yourself.
Oh God.
So I don't know if this is going to be possible. So you need to shuffle your deck.
I still have to open mine.
I have to unwrap mine too.
And make sure to remove the jokers.
I thought you said that you were all learning probabilities.
Oh, yeah, but
We will
would-
bet an eternity. We'll bet money here, and we'll see whether or not we get all winners.
Well, that's what I'm saying. I'll turn on camera if I can make money.
Okay, all right. We'll do on camera drawing, and we'll see what the number is. How about
God.
that?
Oh God.
Okay. Or maybe you can go into a breakout room and check each other's work.
Are we doing triple or nothing?
What's that?
Triple or nothing?
Triple.
Just go all in and then triple it.
You're crazy, John.
I'll give you double odds. How about that? Because I know what
Ooh.
the probability is here.
This
Oh,
box
God.
is hard to open.
It is actually very difficult.
That's why I came prepared and opened it.
I
Has
actually ripped
anyone
mine.
even rolled the dice other than what I told them to?
I rolled them.
No.
They're rigged.
They're rigged.
Okay.
They're
all right.
loaded.
I guess I needed to give more specific instructions here.
Who else ruined their box opening?
Yeah, I absolutely ruined my box.
Oh no,
Literally, I
it's
ripped
not
it.
that hard.
I ripped it open.
You ripped
What
open
are
the
you guys-
box?
Are you guys
Is it
using your
closed
teeth
now?
or something?
You said to shuffle them?
You
Yeah.
said take out jokers?
Yeah, but first take out, there's 2 cards in the front that are the jokers, and there's 2 cards at the bottom that are just like placeholders. I think one of them has rules on them. The other one just has.
Yeah.
I even include the Joker at this point.
So make sure that your card has 52 cards.
I mean, kill.
Do we count them all individually?
No,
So,
you don't have to do that if you just open it for the first time.
Okay.
And then go ahead and shuffle it, or you can bridge it if you like.
I'm not very good at this shuffling thing, so if I get really good cards, I'm sorry.
You're about to hear me
Everybody-
play 52 pickup. I can't
All
shut
right, we're having fun. At least we're alive. Okay. Are you done shuffling?
yes.
I don't even know. I'm gonna just keep going. I'm doing like the slide thing where you
Just
just kind
throw
of
them
push them
all
into
on
each
the
other.
table. and then like mix it with your hands.
Yeah, you can do the scramble is what they call it, where you just spread them out on the table and then you move them around like that, face down.
I'd have to move so much just to get enough space.
You can put them on the floor too. I mean, they're your cards.
52 pickup.
As you like.
Oh yeah. This feels shuffled. I'm not looking. I'm looking straight at the camera right now.
Okay.
Yeah.
All right, folks. So now what I'd like you to do is I'd like you to not look at the following hand that you're going to deal to yourself.
Okay.
I want you to deal to yourself 13 cards face down and separate them from your pile.
Okay. Do you have a preference on how we get those 13 cards?
Excuse me?
Like from the top or bottom?
If
or...
it's shuffled, it doesn't matter.
Yes, but you'll only ever draw from the top.
Okay.
Unless someone's fanning it out for you and then you grab, we'll always draw from the top.
Okay, deal.
Try to grab from the bottom at a casino, they get really mad at you.
Okay. I feel like I'm playing solitaire.
Have you tried that in a casino?
I think they would just kick you out the moment you like do anything remotely weird.
Where you're like, I only play with my own decks, and then bring your own deck in.
No, they have their own decks there. That's actually how you can get really cheap casino cards. They'll punch a hole through them once the casino's done using them, and then they'll give them away for resale.
Oh, that's fun.
They must be
Okay,
really
folks,
nice
does everyone
decks.
have a hand of 13
Yep.
that
Yes.
they haven't looked at, or did you keep?
Haven't looked. I have not
No.
looked.
Face
Hold
Oh my
down.
God.
Face down on desk.
Okay, on God.
Yeah.
You
Okay, so now I'd like you to bet on the likelihood that you have 2 aces.
Okay.
Hmm.
Do we get to do some math before or no?
I want you to be instinctual here. You
Okay.
just dealt yourself 13 cards.
Mhm.
Okay.
Okay.
It could be any of the cards, or is it one that we pick from our hand? Has to be an ace.
So you're going to, when I tell you, you will flip them up and you'll look at all of them and you'll see whether or not you have 2 aces.
Okay.
So
Uh,
can I talk about it right now, or like not about my results, but like about the probability?
You're betting here, so you don't want to
Oh,
give
yeah.
away whether or not you're confident. You're sending me, right? You're putting in the chat what you think the amount of money you're about to put up is.
Okay.
should we privately send it to you so that way we're not? Oh, never mind.
No.
Well, I already sent it.
No, you absolutely have to send real dollars.
Because we could be influenced by what other people bet, is what I was saying.
Yeah, but
Well,
remember,
maybe-
we do
maybe
this
you
in the
should
classroom
figure
too,
yourself
right?
out.
I write
Oh,
them
I
on the
guess
board.
so. Yeah. Dang. Okay, that's fair.
And I mean, who are you going to trust here?
Yeah. We're all trustworthy individuals here.
Is
This
that
is
it?
how much we're betting.
That's the only bet?
Okay.
Wait. Yeah, turn on my.
Yeah. Do we just like point this at our desk now, or what's the
Yeah, so
plan?
now without looking at them first, I want you to hold them up to the camera
Okay.
Okay.
that I can see yours. Here, let me stop.
Oh, I see. Okay.
Give me one
gotcha.
second. I'm setting up my camera.
Yeah. Give me 1 second. I have to close Minecraft. Okay.
No. Don't accuse me of that.
Hang on. I honestly forgot. Okay, there you go.
I need an external camera.
All right.
Okay.
All right, John, let's see your cards before you see your cards.
I'm gonna grab all of them, and then we're gonna see them together.
Wait,
Did
you
I
have to
get
hold them
any?
higher. You
I
have to
got
hold them
one, I
higher.
think. Oh,
Your name's in the way.
sorry, my bad.
Oh yeah.
I got one. I
You
lost
got
20
one.
bucks. I think I lost 20.
Keep going.
Oh.
I think that's it. I love that it's
Oh,
blurring out.
sorry, John.
Yeah,
You
Okay,
got
so-
almost all the 4s though.
I did not shuffle well at all. I just want to say that. I'm so sorry.
okay, and Trinity, what do you got?
I don't know. I'm scared. Let's see.
Here. All
Oh,
right,
there's-
well, we got one.
Oh.
oh no.
Two.
Oh, no.
All right, Trinity wins.
Nice.
Damn it.
That's nice.
Anyone else?
Oh
Damn
yeah,
it.
me. Let me see. Wait, just looked at this camera. Let's go. Okay.
I like that you could see my water cooler in the back. That's good.
You could have told me that was like an aquarium and I would have figured that, and like I wouldn't be able to figure it out. All right. Here it is. One card at a time. Got the fuck. I got turn off the blur.
You gotta get
I'm s-
closer, Rolando.
No,
Hold
I just gotta
the-
turn off the blur. Don't blur my background. See, look at my messy bed. Anyway, 6.
No. Whole thing.
Yeah, I'm a little suspicious
Four.
when he's
That's
like,
fair, that's
look at
fair.
the cards that I want you to see.
Yeah.
All those jacks together. Too bad we didn't ask for jacks.
Yeah.
I'm so boned. No, not even a single ace.
All right.
Dang.
No. Life sucks.
Okay, so Isabel, Reed, and Sarah. Why did you not want to bet?
I didn't know what the odds were, so I was just like, I don't know.
And did you look at your cards?
I haven't yet. I can show them.
No, you don't have to show them. Just tell us if you had two aces.
Okay,
Just simply
okay.
one.
I have one,
Uh,
and I have a lot of queens.
You have a lot of queens. Okay, good. So interestingly enough, let's see. 1, 2, 3, 4, 5. Oh, Sarah also has 2. Damn, that would have been perfect. So I'll give you the answer. And the answer is that the probability of having 13 playing cards with 2 aces or 2 of the same, you know what I'm saying, is about 0.2.
Ooh,
yeah, that makes
20%.
sense.
Okay.
That
And-
makes sense.
Before Sarah had her 2, it would have been exactly that from our results, right? Because we had 5 people who drew and only one of them had 2 aces. So, I mean, that would have been a cute little coincidence, but of course is not emblematic of the true probability or the underlying probability. So how do we go about thinking about these underlying probabilities? How do we calculate that in the first place?
So, I think it has to be a permutation.
Yeah, that would make sense, right? We're in the permutation section. That's good.
Permutation.
We want to use
So-
something like that, right? There's 13 something, there's 32 cards, there's 52 cards, right?
Mhm.
Alright. Brian, flip down, either.
Did we actually lose that money, by the way? Just double checking.
Yeah.
Okay.
Yeah, I wrote it in the,
Okay. Because I'm also
Yeah.
keeping track. I have like a little note that I'm writing down how much I have left.
Okay.
All right, so we got, if we're looking for permutations, we have a permutation of, so the top left is the whole and a 13. 2 of them would be aces. Wait, is this? 'Cause we have to start off with like the whole deck of 52, right?
Excuse me?
Do we have to start off with the whole deck of 52 for our probability calculation? Because
Yeah, I mean,
Well,
we had
here's
our
the thing.
holes.
The question is do we have all the tools necessary to solve this?
Yes.
I think we do.
Okay. So let's see if we can break this down for a second. Here's how we want to think about it. We have some number of cards. We have 52 cards. We're going to be dealt 13 of them.
Mhm.
Okay. Of the 13 that we're dealt, of the 52, what are the odds that 2 are the same? You see?
Yeah.
Okay. So let's answer this question because we need something called combinations. Okay. Does it matter what order the numbers are in?
Oh, no. Okay.
No. Okay, so if it doesn't matter what the order is, you get a new letter. You get this one. Okay. This is
For Chris
sometimes,
money.
yeah, I guess so. Chris. Okay, so this is defined as n factorial, oh fuck, over n minus k factorial like we saw before. Okay, okay? But we're going to add here k factorial on the bottom. Now, what are we saying here? We're saying that we don't actually care what order they're in. So therefore, the number of distinguishable permutations is reduced by a factor of k factorial. That is the subset of the original sample n. Does that make sense?
Mhm.
So is this what we were seeing before over here?
No.
Okay,
So we
okay.
were not seeing that with the previous one. The previous one had the number, I think it was 365 to the power of k, which was the number of times that we drew the birthday,
Mhm.
Okay,
right?
okay.
Whereas this one here, we're talking specifically about, okay, you have all of these permutations of how the cards can be,
Mhm.
right? And you draw 13 cards. Okay. Those 13 cards can be in any order. So while your permutations typically would just be, let's see if I can change the colors here. You know, your permutations typically would be just this, right? That would be NPK,
Mhm.
right? So we might say it like this. We might say that NPK divided by K factorial, where K factorial is the number of unique sets within the subset, right? That we don't care about. So we can throw out those additional ones. Does that make sense?
Can you explain that last part about the dividing by k factorial again?
I think generally speaking, these are easier if we think about them in the context of how we use them. This is why I like doing the betting. So let's do the problem and we'll see if it clicks. And if it doesn't, I'll explain it one more time because I think
Okay.
a lot of folks are confused here. So let's do this. Let's ask the first question. How many combinations are there of 13 cards out of 52?
Hmm.
Where the order of the 13 cards does not matter. I'm going to use dark blue because that seems nicer. Okay, so here's the question. 13 cards out of 52. Order is, I don't know why I would do this, irrelevant. Okay, that's horrible. I'm sorry. Okay,
Can
anyone?
we Wolfram?
No. Hold on. Just
Okay.
saying what before you calculate a number, just what are we saying here? Where am I putting? Do I put this in here? Do I put this in here? Do I put this in here? Where do I stick where? So we can understand what we're doing.
I'm pretty sure you consider 13 factorial because the order doesn't matter. So that goes somewhere, I think.
Okay, so the 13 cards do not matter. So this would be our K, because remember that K is always such that it's less than N, which is the sample size.
Mhm.
So where's our N?
And it's top
52.
left of the C.
52, right?
Let's go down.
That's the 13. Okay, so we could then write this as 52 C 13. And another way of saying this is how many ways can we choose C combinations out of 52? Okay, I'm not going to calculate that. You can calculate that separately. So that is all of the different ways that I can calculate or I can get cards out specifically, right? Okay. So I want 2 aces. So I'm thinking about this in the context of probabilities. P is supposed to be something along the lines of NA over NS. So this is clearly NS, right? Because that's all of the different ways that I can pull 13 cards. So what about the numerator? How do I construct this guy?
Would that be just like what we're trying to select? So if we want at least 2, would it just be 2?
That would be really generous, John.
Yeah.
So if this was just 2, right? Then what that would say is that this is, I mean, look at these numbers for a moment here. So this would be
Oh yeah, it'd be pretty
2
crazy.
factorial,
It's
right?
small.
Right.
Okay.
What
I
we
see.
want to think of instead is we want to think of these in the concept space. So go back to your idea of a Venn diagram, okay? And here's the sample space, and all of this is all of the 13 card combinations. So I have to have 2 events occur. Event A, and event B, such that both of these 2 things occur to get this one here. And I'll show you what I mean by that right now. So if I'm going to get 2 aces and only 2 aces, okay, I'm going to get 2 aces. How do I write that in this context?
Is it not just, oh, never mind. I was gonna say 2 out of 52.
Ah, but why did you stop yourself, Trinity? We know for sure that it's 2 down here, right? Because we need 2 cards, and it doesn't matter which aces they are.
So there's only 4.
But there's only 4 to draw from. So now the sample size is reduced. So this would be event A, drawing 2 aces, right? Okay, what about this one? What is event B?
Everything else?
You need the other cards, right? So you have to
Yeah.
draw other cards. Good. So how many cards are there to draw?
There's 52.
11
No.
left.
Oh, yes. And we're talking the smaller sample space.
Yeah.
It would be, yeah, it would be 11.
So we have to draw, 11 more cards out of,
The 13 that we were hoping to draw? Or is that nasty?
No, no.
Out of 42, the whole thing?
Oh, wait.
Ooh, I'm
42?
not sure. Or I mean 52, excuse me.
50? No, 48.
Yeah, like
I said 48, Trinity.
how do we exclude the 2 that we want to get? Okay, hang on. Sorry.
So
Let me
let's
think
remember
about
what
it.
we're doing here. Here's event A. Event A is drawing 2 aces out of the 4.
Oh, so 48.
Aces out of the 4. And the rest of them have to be something else. I can't go back and grab 2 of the aces, because then I'll have
Right.
3 aces or 4 aces. And that's
Right.
not what I want to know the probability of. So what is this out of?
50.
John, did you say 50?
Yeah.
So what if I draw an ace?
49?
Anyone else?
I'm having trouble if we're not supposed to double count or not. Like are we just considering the whole set?
Right. So let's imagine for a moment. You have your shuffled deck, right? The deck is what you're drawing from. You've drawn 13 cards out of it,
Right.
right? Okay. That means in order for you to get this probability, you need to have drawn 2 aces of the 4 that were available. And you need to only draw 11 other cards, none of which can be aces.
Okay.
So what goes up here?
48.
What?
48.
48. There we go. Okay. Now we're
Nice.
cooking with fire.
Nice.
Okay.
Got it.
Microwave the burrito. Okay. So what does the probability look like? How do I write that? And not in numbers, in these funky letters.
The probability of A um
Plus B
and B.
minus their intersection, right? Isn't that what we've already seen?
I don't think. Oh wait, technically, I guess there isn't. Yeah, do I?
Oh, we're timesing them.
Why am I timesing them?
Because it looks like it's some sort of multiplicity thing going on here.
Aren't they mutually? Wait, are they mutually
Uh,
exclusive?
Hey,
Well, they have to be, right? Because we said this sample here is disjointed from this sample,
Mm-hmm.
right? I didn't say 2 or more aces. I said 2 aces, right?
Mm-hmm.
Okay.
Your odds get better or worse for 3 aces?
Having you choose 3?
Yeah.
It gets worse.
It has to get worse,
It
right?
has to get worse. Yeah.
And why does it get worse? Which of these numbers gets smaller or bigger? Let's have a look. Okay.
Yeah.
So let's remember here. Does this one change?
No. No. That'll stay the same.
Does this one change?
It does by a little bit, right? If we're, or no, it doesn't. I'm just kidding. I
So,
lied.
so the scenario is that you draw 3 aces into the
Yeah.
13 sample, or
Yeah.
Okay.
Oh yeah, it does change. Then your K is gonna be affected. So now it's 10.
Right. So K goes down to 10. And
Uh-huh.
what about over here?
That K goes up by 1.
Right. So let's go back and we'll look at that here, right? So here's how it's written. N factorial is not changing. It'll be 4 and 47. Or sorry, 4 and 48 for those two. And then it'll be K that's changing on the bottom. And I'll invite you to write those numbers out. You'll see it fairly quickly. Which one of those is larger? Is the probability of getting 2 aces or the probability of getting 3 aces higher?
I mean, intuitively, I would say that getting 3 aces would be.
But
the
hold on,
hardest.
right? I intuitively said, and now we're looking at the numbers, right? And John, I just want you to, cast aside your intuition. We haven't put any money down.
Okay.
We'll find out if it's crazy, right?
Okay.
Okay, Trinity, what you got?
I didn't get anything. I'm over here scribbling.
What was that?
You're scribbling. I'm trying.
You're scribbling. Okay.
Yeah.
That's
I'm just writing a lot of factorials right now.
So keep in mind, we only want to look at the difference between the two, right? We only care about what is different between the two. So if, for example, you wanted to compare them, right? Is the aces that we're drawing from changing? No. Is the normal cards that we're drawing from?
Yeah, the normal. Yes.
No, the normal cards are not changing, right? There's still only 48 normal cards. I
Is
just
it?
want 3
Oh, yeah, my fault. Okay, yeah.
Yeah,
How
so
much we're
this
actually,
one
our
goes
hand is
up,
changing.
and this
Got it.
one goes down. So those are the only things we have to change in our calculation.
Got it.
Does that make sense, Trinity?
We're talking about for A, drawing 3 aces, right?
Yeah, so the question is, what happens for 3?
Okay.
of the 3 aces.
And I'll even put it up here. So 4C doesn't change, but this becomes
A 3, yeah.
anyone else online get it?
I just wrote it, but from what I'm seeing, like if I just look at the 4-3 combination,
Mm-hmm.
it reduces to 4,
Yeah.
Mhm.
and the one above reduces to 4-2 combination reduces to what do you call it, 12. So I'm already seeing just from those first two that the first combination that you're doing before you actually like multiply to anything else, there's already like a drastic change between like how much it's changing by.
Okay, so how much did this one change by, John?
So
Change by 2.
yeah, so it was, I think 4C2
Mm-hmm.
that reduces to 12, and then so that's the top one, and then 4C3 is just 4. So it's a factor of 3 that it's getting smaller by just from that one term that we have to consider.
But this one's gonna help us, no? So what's this one?
I didn't solve it, but it's 48 factorial over
Yeah,
37
it's a big
factorial.
one,
Yeah.
right?
Oh,
Yeah.
I have the number for that. It's really
Oh,
big.
okay.
In
Yeah.
scientific notation, it's 2.6 times 10 to the 10. Pretty big.
Okay, and what does it become?
It gets like a little smaller, I would guess. I mean, you're factoring out like what? Another.
Well, let's not guesstimate it here. Let's be precise.
Oh, okay. Yeah. I guess now it's time for Wolf Round.
Is it just 2.6 times 10 to the 10 divided by, oh, no, not divided by.
Nah, it's gonna be a little different.
Okay, Isabel claims to already have an answer. She's smoking y'all.
Nice.
Oh, okay.
So what's this number, folks? Anyone get this number? This is the only one that I want to know right now.
Oh, that
Yeah.
one?
Yeah.
No, that's the 2.6 times 10 to the 10 that I said earlier.
Really?
What's this?
Oh, we thought it was
Yeah.
your.
Yeah.
Okay.
So this is 2.6 times 10 to the 10?
Yeah, because they didn't change whether you had like 2 or 3 aces.
Oh, yeah.
Okay.
Hold on. No, I need to do that. You see that? How that's a 10?
Oh, it's a 10. Yeah, let me go do that real quick. Let me change
I just
that
wrote
real
it
quick.
wrong. I just wrote it wrong.
It's no problem.
Hang on.
For the newly adjusted one, in scientific notation, it's 6.5 times 10 to the 9.
6.5 times 10 to the 9?
Yes.
Isabel says she got 2.3 times 10 to the 10 for this one.
Mhm.
Isabel?
For the 4811?
4810. You got, or
Oh.
4811, you got 2.6.
Mhm.
I think I got 2.3, but it was also times 10 to the 10.
That's okay. 2.3 and 2.6 are the same to me. 10 to the 10 is what matters. So this went down by a full factor of
10.
10?
About-ish.
About a factor of I think this math is not quite working out, folks.
Yeah.
Math is not math.
Might want to double check your Wolfram Alphas here, or if you have it.
Yeah. I was getting different numbers, but I think okay, so for the top one, I
Mhm.
didn't get 2.6 times 10 to the 10. I got 9 times 10 to the 17.
Yeah. Are you okay? So what's
All
your
right,
Wolfram
hold on for
Alpha?
a
Is
second.
it
What's that?
what's your Wolfram Alpha? Because in the numerator it should be 48 factorial, and in the denominator it's 48 minus 11 factorial times 11 factorial.
Is it? Oh, times 11 factorial. I'm doing a permutation. Now that makes sense.
Yeah.
Now that makes sense.
Yeah. Okay.
Got it. There we go.
Okay, well, the point here was to attempt to show how these probabilities are interacting with one another in the top here, but they're not making a difference on the bottom here. We're sort of running out of time, and perhaps that's for the best for everyone's well-being. What I just wanted to demonstrate here is our expectation, of course, would be that the probability goes down, right? And I think Reed and Isabel both said that it went down from 0.2 to 0.14. Now, interestingly enough, I would not have guessed, right, that small a number. So 0.14 and 0.2 in my mind might feel very similar, right? Because if I was going to put $100 on a bet to get, 2 aces, I wouldn't put that same bet on something that feels only 6% more likely, right? And so what I had originally planned to do today was at the end of today, we would do these type style of bets. But I think we're sort of run out of time, and it's obviously more fun to do in person. So maybe if you come early on Wednesday, we'll do a round of betting where essentially we'll be looking for a smaller fraction here. So we're going to choose some number of players who are starting off, and I'll deal you both 2 cards. And you are going to be looking for a specific type of card. And you may be familiar with this game already. You know what this game is?
No.
Anyone in the chat?
Say it one more time.
We're going to be playing a game where you get 2 cards.
Okay.
And I want to
The
know what
only
the
game that I can
probability...
think of is blackjack.
Aha! Okay.
Oh, okay. All right.
What's the
Cool.
probability of getting blackjack on the first try? Right? In a group of, say, 6 people.
Ooh.
Assuming
Okay.
one of them will get blackjack, right? That's what we're going to break down at the beginning.
Are we counting the house? Because
What?
typically the house plays 2, right?
Yes, yeah, but you won't
Okay.
have access to the house. You only know what one of the house's cards are. So we're not actually going to play the blackjack. We're just going to think of this as an idea. Right? You
Okay.
jump into a room with 6 people. What are the odds that someone immediately has blackjack?
Okay.
And remember that blackjack is a specific combination of
The cards?
I don't
Or
know.
you
I
mean
don't
how do
know.
we add up to it?
yeah, how do you add it? How do you get to blackjack?
Oh, I think it's an ace
21?
and a jack.
So I heard 21.
Yeah.
Isabel, that's correct.
Yeah.
21. And that's made how? Sorry, John, you said
Ace and a jack. So
that you
ace would act
definitely
as
need
an
an ace because an ace is an 11.
Oh, or yeah, or anything. Yeah, my mistake. Just any face card with ace. Yeah.
Ah, good. Face and
And a 10.
10. Very good.
Okay, yeah.
Okay. So you should be able to calculate this pretty simply, right?
Yeah.
Okay. All right. Well, let's see if we can play it at the beginning of class next time.
Okay.
Reasonable?
Yeah.
I hope so.
Okay. My office hours are supposed to be in like 15 minutes for about an hour. So I'm happy to chat with folks afterwards. If you want to talk more about, if this didn't make any sense, we can rehash the entire lecture. Reed, I know you had a question earlier, so I don't know if walking through that actually helped. Okay. Yes. Okay, good. Awesome.
Cool.
So then what we'll do here is we'll break off for the day. And if you have any questions or anything else, feel free to let me know. I'm going to jump into, well, I guess I was going to be in the other room, but maybe I'll put my personal room in the chat, and that way both classes can come to it if there's any questions. That makes sense?
Yeah.
Okay. Okay. Thanks, folks.
All right. Thank you.
I know.
Thanks.
Goodbye.